Welcome to our in-depth video tutorial on debugging garbage collection issues in Java. In this video, we will explore how garbage collection works in Java, common pitfalls developers encounter, and how to debug these issues effectively. Let's get started. Before we dive into debugging, it's important to understand how garbage collection operates in Java. Java uses an automatic memory management system that works behind the scenes to free up memory that is no longer needed. Garbage collection employs several algorithms, the most common being the generational garbage collection strategy. This strategy categorizes objects into three generations: young generation, old generation, and permanent generation. Each generation undergoes its own collection process. Young generation is where all newly created objects are allocated. When this generation fills up, it triggers a minor garbage collection, which quickly collects objects that are no longer referenced. If an object survives a certain number of garbage collection cycles, it gets promoted to the old generation. The old generation is collected less frequently, and if it becomes full, a major garbage collection occurs, which is more time-consuming. Finally, the permanent generation holds metadata about the classes and methods. This area is managed differently since it can lead to out-of-memory errors if not monitored properly. Now that we have a basic understanding of how garbage collection works, let's move on to how we can monitor garbage collection activity. To do this, we can use JVM options to enable garbage collection logging. To enable garbage collection logging, you can start your Java application with the following JVM options. This command will generate a file named gc.log where you can find detailed information regarding garbage collection events, including their frequency, duration, and memory usage before and after collection. Now we'll take a look at a sample Java code that may lead to garbage collection issues and how to interpret the garbage collection logs. In this code, we are creating 1,000,000 temporary string objects. Let's run this program while monitoring garbage collection logs. Pay close attention to the GC pause times and frequency of collections. After executing the program, check the gc.log file generated by our earlier command. You would see entries resembling the following. In the log, each GC event is logged with information on whether it was a minor or major collection, the duration of the pause, and the memory reclaimed. A significant number of full GC events or long pause times may indicate an underlying performance issue with memory management. If we notice excessive full GC events, we should consider optimizing our memory usage. One approach may be to avoid creating unnecessary objects, as shown in our example by reusing strings instead of creating new ones. Let's take it a step further now by using profiling tools such as Visual VM or your favorite Java profiler. These tools provide a visual representation of memory consumption and can help you identify memory leaks. To get started with Visual VM, you'll first need to download and install it. After running your Java application with the appropriate options, launch Visual VM and connect to your Java process. Inside Visual VM, navigate to the Monitor tab and observe the heap usage. You can take heap dumps, check for memory leaks, and analyze which objects are consuming the most memory. Let's look at an example where you can visualize memory consumption. Suppose you have a routine like this. In this example, we are continuously adding elements to an array list without bound. You can monitor this with Visual VM while it runs. Over time, you will see that the heap usage steadily increases until memory runs out. Now, let's walk through the strategies to resolve potential garbage collection issues. One approach is to tune the JVM's garbage collection parameters based on your application's needs. JVM options such as XMS and XMX can help you set the initial and maximum heap size, respectively. Additionally, you can choose different garbage collectors by using the XX plus use G1GC, for example, which enables the G1 garbage collector. For instance, if we were to set an initial heap size of 512 megabytes and a maximum of 2 gigabytes with the G1 collector, we would start your application like this. Monitoring the performance after making these adjustments can provide insights into whether the application is now utilizing memory efficiently. In addition to JVM tuning, consider employing best practices for memory management, such as using weak references for caches or services that may not need to retain object references indefinitely. Using weak references allows the garbage collector to reclaim memory more effectively while you can still access the object if it has not been collected. Also, consider reducing object churn by employing object pooling techniques, especially for expensive-to-create objects. Instead of creating new instances every time, reuse existing objects. Lastly, continuous performance monitoring after deploying your application is crucial. Always keep an eye out for any unexpected spikes in memory usage or garbage collection pauses. As we wrap up this lesson, remember these key takeaways. Regularly monitor your garbage collection logs, utilize profiling tools, tune your JVM settings, and apply best practices for memory management. Thank you for joining me today in this comprehensive look at debugging garbage collection issues in Java. If you found this video helpful, please give it a thumbs up and subscribe for more programming tips and tutorials.